Hi, my name is Teena Gerhardt, and I am a math professor at Michigan State University. And I'm going to tell you today about sizes of infinite sets. So this is something that I learned about back when I was in middle school, and I found it really fascinating and intriguing, so I thought it might be a fun thing to share with you today. So first, let me say a little bit about sets. So in mathematics, we like to consider sets, which are collections of objects. Let me give you a few examples of some simple sets. So for instance, I could consider this set that has the numbers 1, 2, and 3 in it. Or I could form a different set by looking at the set with the numbers 2, 4, and 6. Sets don't actually have to contain numbers though. We can put other things into sets as well. So I could form a set that has pig, dog, and cat in it. That's a perfectly fine set. So these are all examples of sets or just collections of objects. Now when we want to study sets, one thing we could ask is how big is this set? What size is it? Or if we had two sets, how can we tell if they're the same size? Well, if we look at the examples that I have here and I ask how many elements are in each set, we could just count them. So here we've got 1, 2, 3 elements in this set. Similarly, here we have 1, 2, 3 elements. This one has 3 elements as well. So these sets, they all have the same size, and we call that size the cardinality. So these all have cardinality 3. Now, let me make a note. There's another way to think about these sets being the same size. So let's look at our lower two sets. We had 2, 4, and 6, and I had this set containing pig, dog, and cat. If I wanted to know if these two sets were the same size, I could count the elements. But alternately, I could ask, can I match up the elements of this set with the elements of this set below it? What I mean by that is, can I come up with what's called a one-to-one correspondence? So for instance, maybe I would correspond the 2 with the dog, the 4 with the pig, and the 6 with the cat. So each element in my top set corresponds to exactly one element in the bottom set, and vice versa. This is called a one-to-one correspondence. And we say that two sets are the same size or the same cardinality if they are in one-to-one correspondence. So I mean the elements of the two sets, correspondence, the elements of the two sets can be put in correspondence with arrows like I just did. So let's look at another example. Let's look at two different sets. So let's consider a set that has elements 1, 3, 9, 13, and a set that has elements, let's say, red, blue, and green. Now, if I wanted to know if these two sets have the same size, I could try to put the elements in one-to-one correspondence. So maybe I would correspond the 1 with blue, the 3 with green, the red with the 13. But now I have a little bit of a problem. So this 9 here, I have not corresponded it with anything in the bottom set. But there's nothing left here. Each of these elements have already been associated to something above. So what we conclude is that these two sets are not the same size. Now it might seem like sort of a silly example because you could have also just counted the elements in the sets, right? This top set has 4 elements, whereas the bottom set has 3 elements. So they have different cardinalities. Cardinality 4 on top and cardinality 3 on the bottom. If we have sets with only finite numbers of elements, like the ones that we've just been talking about, it's pretty easy to tell if they have the same size or different size, because we can either just count or we can set up these correspondences. But in math, we're often really interested in sets with infinitely many elements. So some of them are probably familiar to you. Let's look at some important examples. So first of all, we could consider the natural numbers. So remember the natural numbers, this is the set that starts 1, 2, 3, 4, 5, 6, and I put dot, 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 meaning we keep going like that. So we have all of our natural numbers here. I could also look at just the even natural numbers. So the even natural numbers are the set that starts 2, 4, 6, 8, 10, 12, and so on. So these are both infinite sets, and we could easily ask which of these two sets is bigger. Now, your intuition probably tells you that the natural numbers should have about twice as many numbers in it as the even natural numbers. So intuition leads us to believe that this top set is much bigger than the bottom set. It should be maybe twice as big. As it turns out, our intuition really leads us astray on this one. So two sets are the same size if we can come up with a one-to-one correspondence. And I claim we can do that here. So how do we do that? Well, let's try to do arrows like we did before. So I'm going to associate 1 in the top set with 2 in the lower set. I'm going to associate the 2 and the 4, the 3 and the 6, 4 and 8, 5 and 10, 6 and 12. For any natural number here, if I just pick a natural number x, I can associate it down here with 2 times x. And I claim that that's a one-to-one correspondence. So what did it mean to have the one-to-one correspondence? It meant every element in here gets sent to exactly one element down here, and vice versa. Well, let's look at it. Every natural number does get sent to an even number, gets sent to twice that number. And every even number does get sent to a natural number, it gets sent to half that number. 2 goes to 1, 4 goes to 2, and so on. So what does this mean? It means there is a one-to-one correspondence. And so the conclusion is that the set of natural numbers is actually the same size as the set of even natural numbers. Now this is a very surprising result. I mean, it really goes against what our intuition tells us. So this kind of thinking was originally work of a mathematician named Gerhardt, who lived in the late 1800s and early 1900s. And his work on infinite sets was so controversial that he was subject to all sorts of personal attacks, even from other mathematicians who thought that his work was just really outrageous. Cantor was later recognized as a truly great mathematician. He stood behind his work all along, and people, came to realize that he was right in these ideas. But they were very unsettling for people, and still now I feel like when you first hear about Cantor's work, it can be very surprising. Okay, so now let's consider another infinite set that seems like it should definitely be bigger than the natural numbers, or at least that's what our intuition would tell us. In particular, let's look at the rational numbers. So first, let's remember what rational numbers are. So rational numbers are fractions a divided by b, where a and b are integers, and b is not equal to 0, because we never want to divide by 0. So we want to look at the set of all the fractions like this. In particular, let's look just at the positive rational numbers. So that's going to make this a little bit easier. So let's talk about positive rationals. Those are those where we require our fraction to be greater than 0. So I'd like to compare the size of the set of rational numbers to the size of the natural numbers. So how do we do that? Well, first it would be really helpful if we had a way to systematically write down the rational numbers. With the natural numbers, that part was easy, right? We just listed them, 1, 2, 3, 4, 5, and so on. With rational numbers, it's a little bit trickier because we have all of these fractions, and how do you list all of the fractions like that? Well, let me suggest a way that we could systematically list the rationals. So I'm going to make a little chart here. I'm going to start by listing 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, and so on. Then in the second row, I'm going to list 2 over 1, 2 over 2, 2 over 3, 2 over 4, 2 over 5, 2 over 6. And you can probably see the pattern in how I'm listing. In the next row, I'm going to list 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5, 3 over 6, and so on. Let me put a couple more rows in here. 4 over 1, 4 over 2. Fill in following the same pattern. Maybe I'll put one more. 5 over 1, 5 over 2, 5 over 3, 5 over 4, 5 over 5, 5 over 6. And we would continue in this way. So the dot, dot, dots mean I would continue listing in the way that I've set up. Now we can see that any positive rational number will be somewhere in this picture. If I consider the rational number a over b, that number is going to be in the 8th row and the bth column. So any rational number that we pick, no matter how big or small, it's going to be in this picture somewhere. So we've got them all. You might notice actually we have some of the rational numbers in here more than once. What do I mean by that? Well, for instance, 2 over 4, that's the same fraction as 1 over 2. It's 1/2 when we reduce it. So 1/2 is actually listed here more than once. I would like to have everything listed just once. So I'm going to go through and cross out anything that's repeated. So I'm going to cross out extra copies. So this first row is fine. In the second row, 2 over 1 is okay, but 2 over 2 is the same as 1 over 1. So that one's extra. 2 over 3. 2 over 4 is 1/2. 2 over 6 is the same as 1/3. In the next row, 3 over 3 is 1 over 1. 3/6 is 1/2. Down here, 4 over 2 is the same as 2 over 1. 4 over 4 is 1. 4 over 6 is 2/3. And in the bottom row, 5 over 5 is the same as 1 over 1. So we could go through our whole picture that same way, crossing out all the extra copies of rational numbers that are repeated more than once. Now, why did I organize it like this? Well, my goal is to somehow list the rational numbers in the same way that we are listing natural numbers. So I'd like to form a list, but I need to figure out what's going to be first on my list, and second, third, fourth, fifth. I'm going to use this picture to figure that out. I'm going to start in the upper left-hand corner with 1 over 1. That's going to be the first item in my list. Then I'm going to go to 1/2, and I'm going to go down this diagonal until I hit this first column. This will be the second item in my list and the third item in my list. To find the fourth item, I go back to the top and again down the diagonal. So this will be the fourth item in my list and the fifth item. Then back to the top and down the diagonal. When I hit the first column, I go back to the top and down the diagonal. Then back to the top and down the diagonal. I could keep going through the whole picture in this manner, and you can see that I would hit all of the numbers in my pictures if I keep forming these diagonals like this. What do the diagonals mean? Well, I want to form a list. So I want to list all of my rational numbers. So remember, these are just positive rationals. Maybe I should note that. So I'm going to list all my positive rational numbers. And my diagram here tells me how to list them. I'm going to list 1 over 1 first. Then I'm going to list 1/2. Down the diagonal, I get 2 over 1. I go up to the top and I get 1/3. Then the next thing I hit is 3 over 1. Then 1/4. 2/3. 3/2. 4 over 1. And so on. The purple arrows tell me how to form my list, how to list the rational numbers. And all of the rational numbers now will be on this list. Note this list is kind of in a weird order. It's not in numerical order. I have 1, 1/2, then 2, then 1/3, then 3. It's a different order. They're not just in numerical order. But this order will capture all possible fractions. Now let's compare it to the natural numbers. So the natural numbers 1, 2, 3, 4, 5, 6, and so on. So here are my natural numbers. And we want to ask if there's a correspondence between the rational numbers and the natural numbers. Well, let's just associate it like this. Let's send 1/1 to 1, 1/2 I'm going to associate with 2, 2/1 with 3, 1/3 with 4, 3/1 with 5, and so on. The 7th element in my list, I'm going to associate with the number 7. The 8th element with the number 8, and so on. What does it mean? Well, all of the rational numbers are in this list, and I can associate them in a one-to-one fashion with these natural numbers in the list below. This gives us that one-to-one correspondence we were talking about earlier. So what does that tell me? Well, amazingly, I mean, this is just so surprising, but what it tells me is that the set of natural numbers is actually the same size. So this set is still the same, oops, I can't spell, the same size as the set of positive rationals. Which is crazy. I mean, that means that there's just as many natural numbers as there are positive fractions, which is so surprising. And it didn't matter that I restricted to positive rationals, so I did that just because it makes it a little bit easier to explain. But it's also the same size as all of the rational numbers, not just the positive ones. So you might then think, maybe all infinite sets are the same size. I mean, if the natural numbers are the same size as all of the fractions, maybe there's just one size of infinite sets, and that's it. But actually, that's not true. So not all infinite sets are the same size. If we look at the set of real numbers, so the set of real numbers is bigger. It's bigger than the set of natural numbers. So both of them are infinite sets, but the set of real numbers, its size is a bigger size of infinity. But that is really the subject of another talk. So I will finish with that, and I hope that I've convinced you this is a really interesting, cool, sort of mind-blowing area of mathematics that's fun to look into.